So if you're visiting the class here as part of the campus preview weekend, welcome. This is a course called Computation Structures, which most majors in the ECS department take. It's all about sort of how to build digital systems, and we're in the middle of building ourselves a neato computer. So I hope you enjoy the tour. If you're not here because you're part of CPW, but because you're a student, remember Lab 5 is due tonight. So different treats for each of you. So let me start with a story. So the story really is what qualifies as a big number. So when I was young, your age, I worked on computers that had addresses that were either 16 or 18 or 20 bits big. And that was considered a lot of memory. So this is somewhere between 65,000 words of memory or bytes of memory and maybe 1 million words or bytes of memory. And it was considered a lot because I can remember very proudly the day in which 1 million words of memory for the PDP-6 arrived, or maybe it was the PDP-10, on the 9th floor of Tech Square. It was called a Moby, because that was, it was like 2 big racks full of memory, and it cost $1 million, and it was clearly, sort of all the memory one could ever need. So, but as memory prices drop, so this was considered, this is, we're cooking with gas here, guys. This is a lot of memory, and we were able to run, incredibly big programs. So the years passed, and the prices of memory dropped, and what counted as a big program started to change dramatically in terms of a data set that we wanted to process. We were doing integrated circuit designs, and simply the number of transistors. If we had one word or a little record representing each transistor on a chip, we clearly couldn't really represent it in a machine that only had a 20-bit address space. So we were very happy when machines with a 32-bit address space came along. And my goodness, that's 65,000 times the address space we had only moments ago. And the thing about 32 was it was clearly big enough for all time. I mean, it was 4 billion. I mean, it cost $1 million for one of these. So 4 billion, that just seemed at the time, okay, now that will be the architecture I'll use for the rest of my life, and happily so. Now, of course, your cell phone has 4 times the amount of memory. You got 16 gigabytes in your cell phone, much less 4 gigabytes. This can address 4 gigabytes. And so now, we fast forward, about 3 decades, and now, sure enough, we have a new computer architecture, which is 64 bits. And I'm experiencing a sense of real deja vu here, because now people are saying, clearly, that's enough for all time. Right? For sure this time. This, of course, is 4 billion times bigger than this. Right? It's another 32 bits of address space. And, we'll never have to change again. Right? So I hope you sort of sense what's going on here, is that every 30 years or so, somebody stands up and what seemed to be an impossibly large, isn't this enough to address every atom in the universe sort of things? Not quite, but do we need to address every atom in the universe? What we're discovering is that there's a sort of trend over time that there's these sea changes in architectures where we suddenly need more address space. And in fact, maybe someday we'll get smart enough and stop picking fixed numbers for addresses and to go to some more flexible address scheme that can be, in a sense, expand infinitely large. Can you think of an address scheme that you probably use every day that conceptually can address an infinite amount of information? When you type in a web URL, right? I mean, that's an address which you can sort of make as big as you need. You can always add more characters to it to get to, provide more detail and stuff like that. So maybe computer architectures will make that transition someday. But meanwhile, at least in this course, we're talking about picking a fixed amount of computer address. And as this slide points out here, the real death of a machine comes when you suddenly realize that you haven't made the registers wide enough to accommodate more memory for the program to address. And so you pretty much have to throw away the existing architecture and come up with a new one. Now, it could be a very simple transformation. I'll just make all my registers and data paths. I'll change all my 32s in my beta design to 64s. But inevitably, there's some challenges that come up when you add 4 billion times as much addresses. And some of those challenges we'll look at today. But you tend to have to rethink the computer architecture from ground up. OK, so 3 decades from now, one of you might be standing down here in front of the class and reliving this story. Of course, you'll have to leave more room on the board as you carefully explain why 128 is absolutely the largest number of address bits one will ever need. OK, why do we want so much address space? Well, one thing we want to do is to make sure that we keep an abstraction between sort of the addresses our program uses and the actual amount of memory plugged into any particular machine. So some of you have 4 gigabyte laptops, 16 gigabyte cell phones, 8 gigabyte desktop computers. And typically you want to run your program on all of those. So at some level you would like to come up with a scheme for writing your program and it should just sort of happily generate addresses wherever it's running. And we need to have the hardware accommodate the type of addresses that are being generated by your program, and if you will, adapt the addresses the CPU is generating into the appropriate physical addresses for whatever machine that you happen to be running on. So right at the outset, what we're going to do is sort of come up with this notion that we're actually thinking about maybe 2 addresses. One is a CPU address. I'll come up with a fancier word for that in a second. Okay, which is the address your program generates. And over here is a physical address, which is the address that you actually send to the DRAM chips, SIMs that you bought. And the idea is that there doesn't necessarily have to be a strong coupling. Somewhere in here we may do some sort of transformation between the CPU address and the physical address. Your program, when it runs, often it needs to grow the amount of memory that it's using. So typically, when we start a program, we don't give it access to the entire address space all at once, particularly a 64-bit program. I mean, that would suddenly require more memory than lives on the eastern seaboard. And so we don't really want to say, okay, any of those addresses, ask and I'll give you an answer. So what we do is typically make only a certain number of the addresses you can ask for valid at the start, but then you can ask to increase the range of valid addresses. So there's a whole bunch of addresses, particularly in a 64-bit machine, which your program could generate, which you'll get basically a memory address error because you haven't asked for them to be accessible. Okay, so what we want to do is to have some way of having a very large address space, but sort of grow into it over time. And then finally, we're going to use regions of our address space sort of sloppily. And here's a great picture that sort of shows you how we might use regions of an address space. Typically, there's a certain sort of a fixed size set of region of a program, a running program, which represents the code. I mean, the Chrome or whatever it is you're running. The arrays, the static arrays that Chrome needs, the variables that the compiler has put off in main memory, wherever it is. And then this part you can sort of know at compile time the size of this region of memory. And some of it may, in fact, be read-only. So most of the programs you run use, for instance, the C runtime library. And in those cases, there's no reason to have 15 copies of the C runtime library for each of the programs, for the emailer and for the browser and for all the different things that you're running. And so, in fact, you make the code read-only and you figure out a way to share one copy of that code amongst all the users. So you don't waste physical address space by keeping redundant copies of things that are read-only. Then there's a stack region, which, as we know, grows as we do nested procedure calls. And we use that to store the activation records of the currently running program. And finally, there's the heap. So whenever you allocate a data object in an object-oriented language, or you call malloc in C, or you say new in Java, or whatever it is, you basically go off and you say, give me a new little chunk of memory, please, and the heap can grow. So we have these two regions that can grow. So typically we put this at one end of the address space, the heap, and the stack at the other end of the address space on top of the statically allocated addresses. And then we let them, and the middle is no man's land. In other words, if you ask for address here, if you haven't arranged with the operating system, it'll punch you in the nose and say, I'm sorry, your program made an illegal memory reference. But you can ask to grow the stack, or you can ask to grow the heap, and they start using addresses in the middle. So it's convenient to have a big space to grow into for big programs, but meanwhile it may be for small programs, we simply don't worry about the addresses in the middle. We don't make them accessible to the program, so they don't take up much in the way of physical memory. Okay, so we really can't bound any of the usage, and in fact, for most programs, there's a huge portion of even a 32-bit address space that we tend not to use. So we'd like to have a scheme for dealing with addresses and their mapping to actual locations in memory that can accommodate the sparsity. And in fact, at any given time, because of this locality thing, we may not, in fact, be using, for example, all the pieces of code. They may only come into play when you click the special button on your browser and they suddenly says, oh my god, I got to bring in the MD5 sum generator. And so rather than loading that right off, I'll load it later when you actually start using it. So we're going to expand the memory hierarchy. This is the picture we saw the other day. We have a fast cache whose cycle time is commensurate with the needs of a gigahertz CPU. And then we have the big dynamic RAM that's storing most of the information in your program, at least the parts of the physical address space that you're currently using. And that was slower, right? Here I'm talking a factor of 3 to 20 times slower, and the cache is here to hide the long latency of the DRAM. But the DRAM is nice because it's low cost. So we're trying to get some reasonable cost system that pretends that it's mostly fast, and we saw we could be reasonably successful at that if we design say an 8-way set associative cache to deal, and maybe even a little hierarchy of caches, level 1, level 2, level 3, to sort of deal with hiding the latency of the slow dynamic RAM. Today we're going to add another level, the disk, which, as you can see, is somewhat slower, 10 to the 4th to 10 to the 5th times slower. Okay, so now you can sort of see that you can say, well, the disk can hold everything I need. On the other hand, I really don't want to be accessing disk much, because all of a sudden I take a penalty of 10,000 times going out to disk, right? It takes a long time for this mechanical platter to spin around and for us to move this head in and out. It's very, that takes on the order of milliseconds, and I'm executing instructions on the order of, nanoseconds, or, even hundreds of picoseconds these days. And so this idea of going to disk is nice from a capacity and non-volatile storage. Does everybody know what I mean by non-volatile? Does that mean it doesn't burn, Chris? No, so non-volatile just means storage that will remember its values even when I unplug the machine. Right, so typically it involves some sort of little magnetic medium where you actually are fooling with the little magnetic domains on the magnetic material, and those little magnets will stay polarized correctly even after you unplug your machine. Okay. So we're going to introduce this notion of virtual memory, and what I'm going to do is I'm going to rechange what I used to call the CPU address. I'm going to rename that. I'm going to call it the virtual address. So the virtual address is just a fancy name, computer science name, for the address that's generated by your program as it runs on the CPU. The physical address is what the main memory system actually wants coming over those signal wires to the memory chips. And in the middle, we're going to put a memory management unit. And its job is to translate virtual addresses into physical addresses. And the notion is that conceptually, it's a complete mapping. Every virtual address potentially can be mapped into a physical address, but in practice, that mapping is not complete at any given moment. Only some of the legal virtual addresses Okay, you can sort of see the cores actually have a corresponding physical location. And what we do is the MMU is responsible for mapping some of those. And if I access a region of my virtual address space that does not have a valid mapping to a physical address, I create an exception. I basically say, whoa, it's not in memory. Here's software, you deal with it. The operating system's job is now to figure out, oh, well, you're accessing a page that I didn't, does an address that doesn't exist. Maybe it's on disk. I'll copy it in for you and find a place in physical memory for it. Notice, however, that there's no correspondence between the if I ask for address 0, that doesn't have to line up with physical address 0. And in fact, it could line up with some other region much farther in memory. Everybody sort of happy with that? Now, we could map each byte. We could build something. So we'd have to have a huge, we say, look, you ask for any particular byte, I'll go look up where it really is in physical memory. So that would mean my memory management unit would have to translate any one of 4 billion different addresses into 4 billion physical addresses, or at least tell me that. So it's a big table, or tell me that I don't have such a mapping. So it's a huge table, and that's not going to work very well for us. So the first thing we're going to do is to divide memory up into what we call pages. Not a very complicated word, it's just a collection of contiguous memory addresses. Typically pages on 32-bit machines are on the order of 8K bytes or 16K bytes, something like that. Okay, on 64-bit machines, one of the ways 64-bit machines deal with the very large address space is they use pages that have a couple million bytes on them. And what I mean by dividing up the memory, what we're going to do is to take the address, and some amount of the address, the low order bits of the address, will be the page offset. That'll tell me where in the page I'm trying to get to. And the rest of the address will be the page number. So it'll tell me which page I'm looking for. Right, and where exactly this boundary is one of the architectural parameters of the machine. Okay, so the notion is I'm going to have a map that will tell me, well, I'll get to that. All right, so what's the notion of demand paging? So I'm going to click this up, but then I have an actual demonstration. Wow. I used to love demonstrations. The demonstrations I loved were much more sophisticated than what I'm doing now. So here's all my pages. And initially they're on disk. Now, what a demand paging system does is you say, okay, I'm going to start running my program. PC starts at 0. I need, the information at physical page 0, at virtual page 0. So I'm going to go off and read it off of my disk here, and I'm going to bring it into main memory. And I don't necessarily have to bring it in to physical page 0. I could, I have some other pages, but I find a page, an empty physical page, and I simply say, okay. And then I set up my mapping here so that when you ask for 0, you end up in this physical address. And in fact, that happens for all the 4,000 bytes or whatever it is on this page. Everybody happy with that? Your program runs some more, and pretty soon you do a subroutine call that calls the C library, which is farther up in your address space. Well, I'm going to page that in from disk, and that can show up in physical memory. Notice that the order of pages in the virtual address space don't necessarily correspond to the order of pages in physical address space, right? They can be higgledy-piggledy. I just have to make sure I remember in my mapping, if you give me a particular you ask for a particular virtual page number, where in physical memory I put that. Everybody sort of happy with that? Okay, so that's what demand paging is. I'm going to bring stuff off of my nicely organized array of pages on disk, okay, organized so I know where to get them, and then I'm going to simply bring them into memory and slowly fill up all my pages, all my physical pages. Yes, sir?
So on start of a computer, it takes so long to start because it's doing that for a bunch of programs.
Exactly. The first time you type Python, you drum your fingers and say, what the hell is going on? The second time you type Python, it seems instantaneous. The point is that it's already paged in, that's the word they use, paged in all of the interesting pages of the Python interpreter, so they're there in physical memory and ready for you to use. Yes?
So all the previous times we've been talking about addressing with
We have always talked about addressing as the address the CPU generates. And today, we've named that the virtual address. Now you're building a machine which takes the CPU address and wires it directly to main memory. So the Lab 6 beta that you're building does not have an MMU in it. But you'll see that every machine since, you know, somewhere in the mid-70s or even earlier has an MMU for lots of good reasons, which that's what we're exploring today as well. Now what happens if I need to bring in something and there's no room in physical memory? So here I filled up physical memory. Now I need to bring in this page. Well, we've faced this problem before, right? What do we need to do? We need to throw something out. What should we throw out? Random. Okay, random's a good choice. What's another choice? LRU. And in fact, typically, most of the paging algorithms are LRU. So I take the least recently used page, I guess that was this one, and I put this. Do I need to put it back on disk? Under what circumstances do I need to put it back on disk? I mean, there was a copy on disk. If I had done this right, I would have had another stack of these because I just made a copy of it into main memory. When do I need to actually copy it back onto disk? If it's changed, right? So maybe one thing the MMU should do is not only perform the mapping, but keep track of whenever I do a write to a page, the fact that it's changed, and that's what we call a dirty page that will have to be written back. So you'll see that appear in a little bit. So we have a very simple way of designing our memory management unit. It's a table, and you index the table using the virtual page number, and what comes out of the table is the physical address. Right? So it's just a table of physical addresses. How many entries are there in the page table? I need one entry for every virtual page. Some of the entries have a valid, you can see down here, I have this so-called R bit, the resident bit. Okay. If the resident bit is 1, that means that if I'm asking for virtual page 0, I actually have a corresponding physical page. I check the R bit in the 0th entry of my page map, and I say, aha! And then I just use whatever number appears here as the high order bits of the physical address. The page offset just flows right through. Everybody sort of happy with that? Very, very naive, simple implementation. Okay, but depending on how many virtual pages I have, the page map itself may be quite large, and we'll talk more about that in a second. And here, by the way, you can see the dirty bit. We've allocated room for the dirty bit. So typically a page map has these two control bits, a dirty bit and a resident bit, and then the physical page numbers. And you can see whenever the R bit is 0, that means for that particular virtual page, we do not have a corresponding physical page, and that'll generate on the hardware what's called a page fault exception. Okay, so that's the page map. You notice there's a lot of similarities between this and the cache, right? Mostly it's a matter of, first of all, that we tend to, the chunks of storage we're dealing with are thousands of bytes instead of maybe just a small block of words. So we're moving, in these big pages in and out of disk. In fact, we may actually move multiples of pages in and out of disk for much the same reason as we did big blocks of words in our cache, because the disk has lousy latency but reasonably good throughput once you've got the head in the right position. So maybe we should bring a bunch of pages in when we're doing it. So we have large pages in RAM, but there's a lot of similarities between these two schemes. And you can almost think of main memory now as being a cache for what's on disk. And that analogy will stand you in good stead so long as you remember that the miss time is huge, much, much larger than it is when we missed going from the cache to physical memory. Okay, so this is sort of the hardware view, this notion of this hardware page map. Think of it as just a big piece of SRAM that has this number of bits in each memory location, and it has enough memory locations to provide a one-word entry for each virtual page. So one entry per virtual page. And we have the R bit that tells us whether the mapping is valid or not. So 1 means that I can produce a physical page number and complete the access to main memory. And the 0 means that I'm sorry, that's currently an invalid address. So I don't have any, doesn't live in main memory. So either I have to get it from disk, or if it hasn't been allocated to you at all, I'll bitch and either maybe I'll allocate it to you automatically in the case of a stack access, or maybe I'll simply give you a nice blue screen and tell you, sorry, just reboot your machine. Okay, and the dirty bit is remembering that if we change any of these pages, when we replace it as part of our replacement strategy, as we bring more pages in, we actually will end up having to rewrite it to disk so that the copy of the pages on disk will always eventually be correct. We won't lose any information that's been written to a page. Now the 6.3 view, you can think of this as really a couple of subroutines whose job it is, their translation. Their job is to translate virtual to physical addresses. So I bring in the address segmented as a virtual page number and a page offset. And what this subroutine's job is its job is to produce a physical address back. So this is like a procedure call that says, here's a virtual address organized as a page number and offset. Please give me back a physical address that I can send to memory. And then this is the access into the page table, checking the resident bit, and if it's 0, producing a page fault, otherwise using the physical page number information and concatenating it with the page offset to form the physical address. Page fault is sort of this, is handled separately down here. And typically, this part here, this virtual to physical address translation, is done in hardware, so it's fast. And then page faults really are a synchronous exception to the running of your program. And then we go to some sort of operating system routine whose job it is to figure out the more complicated process of finding the page on disk, figuring out what page we have to get rid of, and if so, write it out, so forth and so on. And if you actually look at this code, you'll see that what that code is doing. It's selecting the least recently used page. If the dirty bit is 1, it writes it back out onto disk. At that point, the resident bit for the LRU page is we picked a, sorry, so let's see if I can be clear. I is the virtual page number of the least recently used page. So we're looking in the page table, which is, of course, indexed by virtual page number. And what we're doing is we're sort of cleaning up the database for that particular virtual page. If it's dirty, we write it out. And after we've written it out, we say that page is no longer resident because that's the one I'm moving out. Then I go off and I'm going to use that. I'm going to go find out the physical page number that it used to live in, and that will become the new home of the page that I really wanted. Right, so when you saw me swap out the one down here, this code, this procedure that you see here is really doing all the bookkeeping associated with updating the MMU state that corresponds to that swap. So it's just something you can sort of puzzle through a bit. Any comments or questions about that? Yes? Crash.
You can decide whether if the R bit is 0,
Yes.
whether to send the fault or to actually fetch it from the
So according to this balance, if the R bit is 0, you cause a fault. The response to the fault, in other words, what the operating system will do, that depends on a bunch of bookkeeping that it's doing in software about whether that address has been allocated to you or ought to be allocated to you, or whether it's just an illegal address. And that's just part of the bookkeeping associated with the operating system. And we'll be spending some time talking about that level of bookkeeping in the next couple of lectures. Okay, so there's a bunch of arithmetic associated with pages. So there's sort of 3 different numbers, right? There's a number of bits in the page offset, the number of bits of virtual page number, and the number of bits of physical page number. And there's all these sort of mambo combinations here. The big thing to keep in mind is that I need 2 to the v entries. I need 1 entry for every possible virtual page number. So if I have v bits of virtual page number, I have 2 to the v different combinations of those bits. So I have 2 to the v different possible indices into my page map. So my page map can get big if I choose my page size to be small. Okay, so down here we talk a little bit about well, on the beta and certainly on machines of the not too distant past, the entire virtual address was 32 bits. The physical addresses have been changing over time. It used to be that, machines that, you bought a decade ago, could only address a couple gigabytes of memory. Modern machines can probably address, they usually now are about 2 to the 40th. They have 40 physical address bits, so they can address, so let's see, 4 gigabytes is 32 bits, so 256 times that. So modern machines can address about a terabyte of physical memory. The latest generation of machines have 48-bit physical addresses, so you can address 256 terabytes of main memory. That seems like a lot, and indeed it is. I mean, but some of these data sets that people are dealing with, particularly in the fields of biology and stuff like that, they're so huge that that number is, sort of what we can afford to put on a machine, but that number is already seeming small in terms of the size of the data sets that we're dealing with, so quite remarkably so. Okay, so as usual, our little friend is asking a pertinent question. Suppose my virtual memory and my physical memory are the same size. Would I even need an MMU? What advantages would I get for having an MMU even in that case? In other words, where I might just leave out this translation. And so think about that. We'll come back to that in a second. Okay, so just to look at some numbers here. Here we have a 32-bit address with a 12-bit page offset. So how many bytes are there on a physical page in this machine, the one that's pictured here? How many bits of page offset are there? 12. So how many bytes are there on a page? 2 to the 12, or?
4096.
Thank you. So one of the things you'll know by the time you graduate as a Core 6 major is the powers of 2 up through a pretty large number. So, okay. Alrighty, so 4096 bytes on a page. How many virtual pages are there in actual decimal? What's 2 to the 20th, roughly? I don't know. 1 million, exactly. So this is 1 million. So how big is this table? How many entries does this table have? Well, it has 1 million pages. There's 1 million pages, so I need one entry for each of the pages. So this is a pretty big table. This is a 1 million entry table, right? And then down here you can see I have an 18-bit physical address, physical page number. So the total number of physical pages is 2 to the 18th, or 256. This is actually a pretty dumb little machine. I mean, your watch probably has more memory than this. Okay, the number of virtual pages we already discussed. We have 20 bits of virtual page number, right? So what I did is I took 32 bits altogether and I subtracted off the 12-bit page offset, right? So that left me 20 bits that had to be on the other part. So together, the virtual page number and the page offset cover the entire virtual address. So we have 2 to the 20th pages. We have 2 to the 20th page map entries. And we need, let's see, so we have 18 bits plus the R bit plus the D bit. So we have about 20 bits per entry. So we have about 20 million bits of information in our page map. That's actually a lot to stick into, that's actually not a small piece of DRAM. So we're starting to say, well, conceptually this was a very clean picture. From an implementation point of view, perhaps this is a little expensive. This MMU, which was meant to be this neat thing, is actually turning out to be as expensive as all my caches, my CPU. Maybe even if you're buying a lot of static RAM, you could buy a lot more physical RAM for the same money. Static RAM is pretty expensive, and plus it's a power hog. Okay, so Plan A, which we'll modify quickly, but at least gets the job done, is to say, well, look, we don't really want to store that page map in a special piece of memory that we went out and bought. What we want to do is we'll just store it in main memory. I've already got lots of bits of memory. I'll just take some portion of my memory, and I'll just make an array in memory, which is the page map. 1 word per page map entry. So I'll have a special register in my machine called the page table pointer, which points to the first element or the 0th element of the array. And then I'll add the virtual page number as an index into that array, and I'll come up with a particular memory location to look at in main memory, and I'll fetch the physical page, then I'll get the page table entry, and then I can complete the translation to the actual physical address, and I can go get it from main memory. So I'm actually accessing main memory twice now, every time I want something from it. Well, on Tuesday, I was moaning about accessing even once, and now I've gleefully just said, well, hell, I'll throw in a second access because I don't want to buy a lot of memory for my page map. So let's stop here for a second. What could we do about this? What could we do to say, well, I sort of like the cost of this, but it's sort of too slow. So what's our strategy for dealing with something that is inexpensive but slow, but we want something that's inexpensive and fast? Yes? Use a cache. Okay, so keep that in mind. Use a cache. Okay, so what we're going to do is we're going to create a little cache. It doesn't actually have to be very big. That actually is, the tag and the data. The tag in the cache is the virtual page number, and the data in the cache is the physical page number. So this cache's job is to sort of, if you're going to use a software term, memoize, to sort of remember physical to virtual page number translations for some small number of pages. It might be 100, it might be 64 locations or 128. They tend not to be very big. They have huge hit rates. They have hit rates in the 99+% range. Okay, so they're fully associative. So this is a place where we do use fully associative mappings. And we have a special name for this cache. It's called the translation look-aside buffer. That's an IBM name, if I remember correctly. We might call it a cache naively, but IBM being IBM, translation look-aside buffer, TLB. So almost all machines implement a TLB, and so that means we only have to go through this sort of more cumbersome access to the real page map only when we miss in the TLB, and that happens for some incredibly small percentage of time. And in fact, on certain classes of the Sun Microsystems processors, if you missed in here, you got a software page fault, and then you use software to go look on the actual, you look in the page table. I think on the Intel machines, there's hardware that does this piece too, this lookup in the page table. So some or all of this is in hardware, and then of course if there is no mapping. So if I miss in here, I check the real page table. If I don't have a valid, the resident bit is off, then I go to software and let it deal with the page fault. Okay, everybody sort of see? So these caches really are, whenever somebody comes to you and says, oh, I have something I need to do, but it's very slow, but it's convenient, I understand how it works, the entire world has information I want, but, getting to it is very slow, but it turns out there's only some information, I'm accessing only a small subset of that information frequently, can I make that fast? And, so caches should be something that, are part of your architectural repertoire, almost no matter what problem you're solving. So fast, slow. Okay, so when you see that sort of juxtaposition, you can say, I wonder if a cache would be a good idea. Cache is, of course, always a good idea. So you know what the symbol is in diagrams for, somebody draws an architectural diagram that has a cache in it. They put this, right? So that's $, right? So you look at a picture of an Intel CPU and you see this $, you say, well, I know I'm paying them a lot of money, but what? So that's just, remember, that's cache. So I wonder if European universities use the euro sign. I don't know. Okay. So here's a little exercise that I'm not going to go through in detail, but something that you have the answers for. You should be able to answer each of these questions, right? So I've given you a little page table down here. I've told you the sizes of things. So let me just make sure we diagram the addresses. So here we have the page offsets. So how big is the page offset in bits? Given the information you see here. How many address bits are devoted to the page offset?
10.
Thank you. And where did you find that number? Yeah, so I told you the number of bytes on a page, so you take the log of that to figure out the number of address bits I need. So if I have a 32-bit address space, how many bits of virtual page number do I have? 22, because virtual page number plus offset has to cover the entire virtual address. How many sort of decimal is 22 pages? About 4 million. Okay. Physical address. How big is the physical address? How many bits of physical address do I have? Well, you're writing, yes. We actually have 24 bits altogether of physical address, but we have 14 bits of physical page number. So you should be, practice sort of turning English into these address diagrams, and then you'll discover that almost all of these simple questions can be answered once you've filled in this diagram. How about this last one? 1804. I want virtual address 1804. I'm not going to work it through, but conceptually, what do you have to do? If I want to actually figure out where in physical memory virtual address 1804 is, what is it I have to do? What I have to do, Chris, is wait until you answer the question. But suppose I wasn't going to answer the question. I went on strike. I need to figure out the virtual page number. So I have a 1804. Sadly, this is not on the X-digit boundary, so I have to turn a bunch of things into binary, because I'm going to use the low order 10 bits of this address as the page offset, and then everything else will turn into the virtual page number. So what is the virtual page number of this address? Well, you can see it here at the bottom of the slide. It turns out to be 6. How do I turn a virtual page number of 6 into a corresponding physical page number? You look it up. I go back over here, and I go down to index 6. It's always 0-based, of course, because we're computer scientists. I didn't start counting at 0. How many things are on the table, Chris? 0, 1, 2, no. Only when I became a computer scientist did I start counting at 0. So I look at index 6, which is the 7th entry in the table, of course, and I see that the resident bit is 1, and that corresponds to physical page number 2. So I replace the physical page number portion of the address, the virtual page number portion of the address with a physical page number. And then I have to reassemble it all in hex. So if we're really kind to you on quiz problems, we will arrange things so everything lines up on hex-digit boundaries. And if we're not kind to you, you get to expand it all out into binary and say, oh, 10 bits and 22 bits. And, okay, so. You know how deep the snow was when I was young? Well, I feel that you should feel some of it too. So, okay. So you can think of the memory map now as this context. It's a context for interpreting virtual addresses. So what I have, if I give you the page map, I tell you everything you need to know to turn a virtual address into a physical address. And in fact, if I wanted to run more than one program at once on my machine, I might be able to have them sort of living together simultaneously. Okay, notice that in this particular instance, I have, if you will, 2 virtual memories that I'm dealing with. One for the browser and one for my email program. And they both have addresses that say, they both start at 0. They were written as if they had the entire machine to themselves, but I'm going to have a different context for each of the 2 programs when they run. And so when the browser says, give me location 0, it ends up at this physical page. And when the email program says, give me location 0, it ends up at a different physical page. Right? And if I had a rapid way of switching contexts as I went from one program to another, each of these programs could all feel that they have, in a sense, the machine to themselves in terms of address space. And by simply quickly changing context, and what do I have to do to change the context? I'd have to go change all the entries in the page map, which isn't trivial, right? There's a lot of entries in these page maps, but we'll solve that problem in the next slide. If I could change the context quickly, I could go from running one program to another, instantaneously almost. Yes?
So some programs would use the same things in memory though, right? So,
You mean shared code?
yeah.
Okay, so that's a very good question. What do you do with shared code? Well, what are our two choices? Our two choices are to make sure that the shared code ends up in the same virtual address space in everybody. And then we simply arrange the context to take, if this is the C library, and this is the C library here, we make sure they all map to the same physical memory. Actually, many libraries are written to be what's called position independent. They can actually run in any location in virtual address space. And so that actually simplifies things a little bit. But that's, we're getting, 6033, you'll learn all about how to deal with some of these more complicated issues. Okay, so the sneak preview really is that we're starting down the path of saying, gosh, we really like this beta that we built, this virtual machine. Seems like this machine, this hardware. But it turned out to actually make running programs in the modern environment where you're trying to do 18 things at once, wow, email, 6004. I know that doesn't take very much, but occasionally you do 6004. What we'd like to do is to say, look, everybody gets their own copy of the beta, a virtual beta. A virtual meaning that what we're going to do is we're going to take the physical beta and multiplex it among all these different tasks. And each task feels that it has an entire beta of its own, has its own virtual address space and everything, its own stack. And I don't have to say, well, what mix of programs do you want to run, and I'll compile them just so. I can say everybody gets compiled exactly the same way. Everybody starts at 0, so forth and so on. So this is going to be the topic of some lectures coming up. Rapid context switching? Well, in fact, if we sort of, for each context, think of that as an extension of the virtual page number, and we use, we sort of concatenate a particular virtual page number from a particular running program with, in a sense, an index for the program, a context number, we can use that, run that through the translation process. So we can think of this as really a huge virtual address space that not only includes the virtual address space for a single program, but additional copies of the address space for everybody who's running. Okay, so we might have, another 8 bits of context, and we'll just treat that as more virtual page number. So then we wouldn't even have to fix the page table. The page table, of course, would be correspondingly larger, but the translation process would run sort of unchanged. And so we can do rapid context switching simply by changing the magic number in this register and going from there. Okay, so here at the end, just to finish up, so far we have a cache and we have a memory management unit. What order should they go in? Should the cache be listening to the virtual addresses of the CPU? Okay, in other words, this process seems a little slow, so this is sort of attractive. The idea, look, if you ask for a virtual address, what I'll do, this is what's called having the cache virtual addresses, right? So the cache, what it has in it is virtual addresses. What the tags are virtual address tags. The numbers are inside the tag field are pieces of the virtual address. So we'll respond quickly whenever we can. What's the problem with this arrangement? Well, when I change context, now I have to flush the cache. Because because when I change context here to run a different program, now a particular virtual address corresponds to a different physical location, a different actual value for a particular address. And so that means whatever was in the cache has to change. If I switch the order of the MMU and the cache, I solve that problem, because now the cache is caching physical addresses. So I've already done the translation to physical address space. The trouble is I have to wait until the MMU process is complete before I know what address to look up in my cache. So that seems to make things longer. But the cache uses the low order bits of the address as indexed to figure out what tag field to fetch when we're using an n-way set associative cache. The MMU uses the higher order bits of the virtual address. If I said physical before, I meant virtual here. This is the virtual address coming from the CPU. So the lower order bits index into the cache, the higher order bits index into the page table. The MMU, while I'm looking up in the cache, the MMU is also looking up the physical address translation. I end up with a tag field coming out here and a virtual page number coming out of the MMU at the same time, basically one SRAM delay. And so if I can choose the parameters of my machine and the design of my cache and the design of my memory map in such a way that that the virtual page number and the information, the index to the cache do not overlap, I can actually run these two in parallel. And a lot of modern machines sort of do that. I hinted right at the beginning of lecture that it may be that these sort of flat address spaces are starting to be architecturally something we want to change. And my guess is that if any of you goes into the field of computer architecture, one of the things that you probably will deal with, okay, is this transition from these large flat address spaces, which is sort of what we use now, to the sort of thing where we're using much more versatile, sort of infinitely expandable addresses. We'll have to figure out how to make that fast and efficient. But you can imagine the conceptual power of being able, in your program, to address any piece of information anywhere in the world, rather than saying, oh, no, that's not in the array, that's in a server in China, and I have to do another part of my program. If it was all part of one giant address space, I could say, fetch that. Might take a little while, but at least it might make my programs much simpler. So there's interesting things to think about where architecturally we're going to go with the notion of addressing information. Okay, I'll stop there. Good luck on finishing off Lab 5. Have fun with the rest of CPW, either as host or guest, and we'll see you next Tuesday. No lecture next Tuesday, student holiday. We'll see you a week from today in lecture.